You have that on your problem set. And then there are other slightly less important models. There's a model of radioactive decay. There's a model of a bank interest, bank account. Various motion models. You know, Newton's law type problems if you can figure out a way of getting rid of the second derivative. Some motion problems. A classic example is the motion of a rocket being fired off, et cetera, et cetera, et cetera. Now, today I have to pick a model, and the one I'm going to pick is this temperature concentration model. So this is going to be today's model. Tomorrow's model in the recitation, I'm asking the recitations to, among other things, make sure they do a mixing problem. To show A, to show you how to do it, and B, because it's on the problem set, so that's not a good reason, but it's not a bad one. The others are either in part one or we'll take them up later in the term. This is not going to be the only lecture on the linear equation. There'll be another one next week of equal importance, but we can't do everything today. So let's talk about the temperature concentration model, except I'm going to change its name to the conduction diffusion model. I'll put conduction over there and diffusion over here, let's say. Since, as you'll see, the similarities, or they're practically the same model, all that's changed from one to the other is the name of the ideas. In one case you call it temperature, and the other case you call it concentration, but the actual mathematics isn't identical. But so let's begin with conduction. All right, here's so I need a simple physical situation that I'm modeling. So imagine a tank of some liquid. Water will do as well as anything. And in the inside is suspended somehow, is a chamber. A metal cube will do. And let's suppose that its walls are partly insulated. Not so much that no heat can get through. There is no such thing as perfect insulation anyway, except maybe a perfect vacuum. Now, inside, so here on the outside is liquid. Okay. On the inside is what I'm interested in is the temperature of this thing. I'll call that T. Now, that's different from the temperature of the external water bath, so I'll call that T sub E. T for temperature, measured in Celsius, let's say, for the sake of definiteness. But this is the external temperature, so I'll indicate it with an E. Now, what is the model? Well, in other words, how do I set up a differential equation to model this situation? Well, it's based on a physical law, which I think you know. You've had simple examples like this. The so-called Newton's law of cooling. Which says that the rate of change, the temperature, the heat goes from the outside to the inside by conduction only. Heat, of course, can travel in various ways: by convection, by conduction, as here, or by radiation, are the three most common. Of these, I only want one, namely transmission of heat by conduction. And that's the way it's probably a little better to call it the conduction model rather than the temperature model, which might be involve other ways for the heat to be traveling. So dt, the independent variable, is not going to be x as it was over there. It's going to be t for time. So let's maybe I should write that down. T equals time, capital T equals temperature in degrees Celsius, and you put in the degrees Celsius if you want. So it's proportional to the temperature difference between these two. Now, how shall I write the difference? Write it this way, because if you don't, you'll be in trouble. Now, why do I write it that way? Well, I write it that way because I want this constant to be positive, a positive constant. In general, any constants or parameters which are physical, have some physical significance, one always wants to arrange the equation so that they're positive numbers, the way people normally think of these things. This is called the conductivity. The conductivity of what? Well, I don't know, of the system, of the situation. The conductivity of the wall, or if the metal were just by itself, it would, at any rate, it's a constant. It's thought of as a constant. And why positive? Well, because if the external temperature is bigger than the internal temperature, I expect T to rise, the internal temperature to rise. That means dt, its slope, should be positive. So in other words, if TE is bigger than T, I expect this number to be positive. And that tells you that K must be a positive constant. If I had turned it the other way, expressed the difference in the reverse order, K would then be negative, have to be negative in order that this turn out to be positive in that situation I described. And since nobody wants negative values of K, you have to write the equation in this form rather than the other way around. So there's our differential equation. It will probably have an initial condition, so it could be the temperature at the starting time should be some given number T0. But the condition could be given in other ways. One could ask, what's the temperature as time goes to infinity, for example? There are different ways of giving that initial condition. Okay, that's the conduction model. What would the diffusion model be? The diffusion model mathematically would be word for word the same. The only difference is that now what I imagine is, I'll draw the picture the same way, except now I'm going to label the inside not with a T but with a C. C for concentration. It's in an external water bath, let's say, so there's an external concentration. And what I'm talking about is some chemical, let's say salt will do as well as anything. So C is equal to salt concentration inside, and CE would be the salt concentration outside.